Welcome again. We are in section 2, monodic categories, and I said on Tuesday that I hope to be finished with this week, but I will not. I will leave out some stuff, but still I won't. As I have, actually, I want to first start with some additions. In 2.9, we had the strictification theorem, and I formulated it by saying that any two morphisms between two given objects which are made out of which are combinations of associated units and their inverses and identities, of course, are equal. One should add the word formal combinations, and the point is that I don't write anything about this to save time. The point is that it could happen in a concrete category. That if I have a large diagram, well, this is now not very large. If morphism like that, where maybe also in the opposite direction. And here actually one uses explicitly that the associated units are invertible. So we cannot leave that out, at least not if we want to get this result. The idea then is to use the pentagon, that's what we have, and triangles to get commutative parts of this until we end up with a pentagon or triangle. And when you analyze that, it can, in principle, happen that two of these objects here are actually identical, not just isomorphic, and thereby the diagram splits up into two parts. And now, if you would have had to use a pentagon which partly lies in this part and partly lies in this part, then we can get into part. Now, this does not, as far as I can tell, happen for any of the categories we are concerned with. In particular, not for vector spaces and not for categories of cobordisms. But it can happen if the category is skeletal or close to skeletal. And on NLAB, there is a detailed proof, even more detailed than the proof in the Planck's book, which also takes up this point in more detail. There was another eraser. Let's see if I take this one. I also got some other references on that, but I haven't checked it out. I will not mention this now. Another addition, which I left out in order to finish in time, is in 231. I had several additions. That's further addition. This was about examples of algebras in monodic categories. And one more example, which in applications is of much interest, is that I have the representation category, we just call it SL2L, where L is a non-negative integer, well, positive integer, say. And concretely, this is the category of a certain type, natural type of representations of the vertex operator algebra associated with the affine V algebra A11, where the level of the representations is equal to L. If you do not know what this means, just take this for granted that there is one can get this as a representation category. In particular, it's a Euclidean category, and the objects in this case correspond or can be the isomorphism classes of simple objects correspond to labels 1, 2 up to L. So there are L plus one of them, and there is a tensor product. I write it directly in terms of the Grothendieck ring, where I have called this well. This is semi-simple. Then I have this notion of classes of simple objects, which I call capital lambda, and I can take these integers, and with this notation for small lambda, and say lambda prime in lambda, the product in the Grothendieck ring that I defined last time is the following. I have lambda minus, in terms of this notation, the sum of lambda minus lambda prime plus 2, and so on in steps of 2 up to the minimum of lambda plus lambda prime and 2k minus lambda prime. If I would leave out minimum here, just lambda plus lambda prime, then this is just the rule for tensor products of the Lie algebra or Lie group SL2. So this is a kind of truncation of that to finitely many simple objects. And note that if I take in particular the label L here, then according to this rule, I have just one term on the right hand side. So it means the tensor product of L with y lambda, YL with y lambda is isomorphic to yk minus lambda. So it's again simple and not just direct, general direct sum of simple objects. And that, well, in particular, L tensor L is equal to 0, and 0 corresponds to the tensor unit. So you see that L is invertible. Let me write YL so that the object K. Often this is called K. Another K. Yeah, that's correct. K is often used for the library, but since I use K all the time for the field, I find it relevant. I have to get this in. So it turns actually out that just like this is for SL2, for any simple or semi-simple Lie algebra, there is an analog of that with rules which generalize this. If you happen to know the rule for calculating tensor products of finite dimensional representations of finite dimensional simple Lie algebras, there is one way to do that, which is very easy to put on a computer also, is you shift the weights of one representation by the highest weights of the other, and then reflect everything into the fundamental Y chamber by Y reflections with minus sign, and you get this truncation by using the affine Y chamber and affine Y groups. And it turns out for these categories, and also in full generality, when you have a null category with invertible objects, then many of the algebras you get there involve invertible objects. And
so the second term in the sum, the 2 should be outside of the absolute value.
Let me see. You're right. Yeah. And then I need a bracket in order not to mix this up with this class here. That is wrong. Now, one gets the following result. due to various people, in particular here of Ostrich, that up to Morita equivalence. And I will not explain Morita equivalence. I think most of you know that, and I think we don't have time to do it. The following is the complete list of algebras in this category. Let me call it CK. No, not C. L, which almost looks like the C. If L is odd, then we only have the trivial algebra tensor unit. If L is in 2Z, then we have the algebra 1 plus y. So 1 is y0, and then here we have this invertible object yl. And in addition, if L is equal to 10, 16, or 28, there are exceptional solutions. In this case, we have 1 plus y6, 1 plus y8 plus y16, and 1 plus y10 plus y18 plus y28. And you see here and here, no, not here, here and here and here, all of these are the invertible objects. So now, in general, the Morita class, these are, in general, algebra Morita equivalent to one of those will have more, but not only general. Always will have more simple subobjects. So that's why one gives those particular representatives. And as I will stress next week, it's for many considerations interesting to have a Morita invariant formulation of statements and of arguments. But for complete calculation, one often has to work with, if one deals with such algebras with up to Morita equivalence, one still has to use a particular representative, and then in this case, this is the preferred choice. So now we continue with the development at the point I ended last Tuesday. I introduced the notion of a morphism of A modules, where A modules, left and right, and bimodules, and morphism of A modules. And I introduced the categories of A left modules, A right modules, and A prime bimodules, which have as objects modules and the morphisms, module morphisms. Exercise check that they are indeed categories. But there is a category with those objects and those morphisms. It is, of course, just checking the definitions. And then the next point will be to use some definition, which I will very often use instead of writing Hom A mod. I will just write Hom A. And also instead of using Hom mod A, I will use the same symbol. So this might be confusing, but we will never use it at the same time for both of them. And instead of Hom A by mod A prime, I write Hom A prime, or if I want to make very clear that this is left and this is right, I put the line. After this is used in very often in the literature. Then I continue with a definition, which has a separate label because I originally planned to have this only later. There's a particular class of A modules, namely the free or induced. We always induce for algebraized free is probably the non-natural term. And this is an A module. Remember, this is an object in C, which I do not write out explicitly here, together with an action morphism. And I denote this thing by int A of X, where the object is of the form, this is now for left modules, for right modules, it's analogous, is of the particular form, a tensor product of X with A, and the representation morphism is just the identity on X tensored with the product in the category. So
this is right model.
Sorry?
Is this right model?
X.
Yeah.
I wrote a right modules here, so
Okay.
then I leave it and do not change it. So graphically, this simply means that my object is now a tensor product, and the representation morphism is given by just the identity and product. And if you do it for left modules, then you just put it, turn this left right. And again, exercise. If I only take the induced modules and take the full subcategory of those, only take. No, this is not an exercise. It's just obvious. If I take only the induced modules and all module morphisms between them, but then I get a full subcategory of but another exercise would be that if the category C is abelian, then the category A mod is also abelian. Next, it's an important aspect of modules where the induced modules, well, in particular induced modules, which actually allows one to do rather explicit calculations in many cases with categorical modules. I don't write, just save time, don't write all the time now what the assumptions are. So if I talk about an algebra A, it's an algebra in a monoidal category, and the monoidal category is called C, unless I call it otherwise. With these assumptions or notations, there are canonical isomorphisms between the space of module morphisms, where the first module is an induced A module and the second is arbitrary, and morphisms in C, where I have X here and the object underlying M at this point, and so remember I had this notation M. We write this as M row if no confusion can arise, and if we want to specify this, we write M dot. And actually, This is easy to show in formulas, but it's even easier to show it graphically. And after I have introduced a bit more graphical formalism, I will actually show the proof. Now, if you look at this, this is nothing but an instance of an adjunction. So we should better rewrite this by using the definition. You have an induction functor int a from C to. I have to be careful. I wrote it for left modules now. So I should have given left modules here. Yeah. This goes to A mod, and which of course sends X to an induced module. Now I write it to and which sends a morphism to identity on a tensor with F. Respectively, the F tensor with the identity for F. You can check that this is a functor, and then there is a specific forgetful functor where I forget the module structure. So I call this U, or if I want to be precise, UA. A mod to C. It shakes an A module and maps it to the underlying object. And which does not is the identity on morphisms. And also there are actually two forgetful functors that are relevant. Instead of A mod, I can also take A in, where this is a int, I should call it, yeah. And so the category which has induced modules as objects. And then the lemma that we have here can be reformulated as simply that the induction functor is left adjoint to this forgetful functor. And once we have the proof of this, we still have to show that that this is a natural isomorphism, but also that one is easily by graphical calculus. So therefore, I now turn to graphical calculus again. Which I already used because I decided to introduce modules before this. So it's a special case of what I've written. If you have A and here M, or maybe I should once write M dot, but usually I will not. We abbreviate this by just drawing M vertical the line and then having A attached to it like that. And if we want to be I want to be very nice, some symbol here. But, it takes time to draw this. I will usually leave it out. And then the compatibility with the multiplication simply says that if I act twice after each other, then this is the same as first multiplying and then acting. And compatibility with the unit says that if I act after the unit, then this is just the identity. This is for left modules and switching or reflecting the vertical line, we get a formula for modules. Now we can look at a proof here. I will define more linear maps from this vector space to this and in the other direction. So we have A int A of X and M, and we have C X M prime. Now we have two categories involved. I want to use graphical calculus. The graphical calculus for one category. We always, in such a situation, use the category we start with and draw pictures in that. And then, if you want to say that this is a really a morphism in a different category, we have to impose or show, depending on what we are doing, that they are actually lying in that space. And what do we do? Well, assume we have an arbitrary morphism F from, and maybe I don't use colors here, then it goes a bit faster, from A tensor X to M. Then I send this to, well, I want something where only M or M dot, this should not be, it should be M. No, let me see. X, yeah, this is X. X like in my notes. Where we have only X here and M here. So there is no place for the A line, but of course we have the unit we can put here. And in the opposite direction, assume we start with a morphism G of this type. Now we have X and M. We send it to, well, we of course have to use G. X and M. And now we need somehow an A line. We can connect this to the graph by using that M is a module. So we take the module morphism here. And then you show that these are each other's inverse. Just indicate this quickly. So in one direction, if we start like that, we have A, X, M goes to this, and then we have to add to this A line. Now this is because if we assume that F is in this space, so module morphism, we can put it below, meaning that, and now I left out a step in my notes. Let me try to, no, correct. I take this a bit lower, so we end up here, and then we use first the unit we just use the unit property to get back F. And in the other direction, we start with G. We send, well, this is almost trivial, so maybe I would not even have shown it. we put it like that, and then in the second step, we add the unit. And then again by the unit property, this is true. And then we are done. No, we are not done.
This is blank. This is blank. The last step of F. This is blank. AN.
Can you see?
Right. On top, right. You also have a. Yeah.
Thank you.
Yes.
But we still have to show that when we start here, this is an arbitrary morphism. What we get, start here, what we get is a module morphism. But that is also easy to show simply because what do we have to show? We have to show that acting here or here is the same thing, but acting here is the same as identity on X and acting with the product here. And then we use the property which will just erase to bring this up. And then in order to show that we even have a junction here, what we do is simply that, and I just do it for one of these manipulations. No, if we are on this side, and now we have not X here but Y with some morphism phi from X to Y, then this is sent to by our prescription to having the unit here. But this is the same thing as the morphism here combined with what we have originally. So whether I first put the morphism here or after the map doesn't matter, and for the other map it's then very briefly, I don't write much about this definition. A semi-simple algebra. I mentioned this at the end last time because it turned out that I implicitly or even explicitly used it. In an abelian monoidal category is an algebra such that the category of modules is an abelian category. And it doesn't matter whether it's equivalent whether we use a left or a right modules. And '47. Everything is completely analogous for co-modules, co-algebras. So left, right, by co-modules, and we get just all the statements and proofs by reflecting the pictures along at the horizontal line. So now we can continue with the general development. Come to the next section, subsection, which is called monoidal functions and monoidal natural transformations. Remember, when we have functors between linear categories, we typically want to be them compatible with that, so linear functors, and we even do not mention that usually. Analogously, if we have a functor between two monoidal categories, C and D, then we are mainly interested in monoidal functors. functors compatible with the structure. But actually, I should already say now one has to be coupled with that. And this will take me a few minutes. But I hope I can do this before the break. So we start with a definition, and later we'll have a slightly generalized definition. So we assume we have two monoidal categories, C and D, with corresponding tensor products, unit associators, and uniters. And if needed, I put labels here. Here I put them up because I need space for other subscripts. But in many, it's very usual to leave out those labels because they are always clear from the beginning. So from the context. So what is a monoidal functor? From C to D. This is a triple. F phi 0 phi 2. Where F is a functor between the underlying categories. Phi 0 is an isomorphism in D from the unit in D to what I get by applying F to the unit in C. And similarly, phi 2 is a natural isomorphism. So a family of isomorphisms, y2, say uv. No, I write xy because I might. Yeah. Which goes from f of u tensor in D, f of, now I write u. Oh. Yes. 2, what I get if I first tensor in C and then apply f. And maybe I write explicitly isomorphism here. So these are the data, and they have to satisfy it should be compatible. This amounts the convertibility of the following diagram, which takes me a little time to draw, and to save time, instead of f of u, I just write fu. And so we start with fu tensor fu tensor fw. And so it's for all u, v, w, and c. And we either first apply phi 2 uv tensored with the identity on fw to get to f of u tensor v tensor fw, and then apply phi 2 again. And now for u tensor v comma w to get to f of u tensor v tensor w, or we use the associator of D, fu, fv, fw, to get to fu tensor fv tensor fw, and then use identity tensor phi 2. I don't write the labels because it should be clear to get to fu tensor f of v tensor w, and then in the second step via phi 2 to get to f of u tensor v tensor w. And then if I compare these two, they differ by the associator in C for UVW as applied to it. And also compatibility with the uniters. I just draw one of the two diagrams, the other one should then be obvious. So if you take 1D and F U, we can use the uniter in D, the left uniter, for FU to get to FU. But we can also apply phi 0 to get to F of the unit of C. So y0 is an identity F U. Yes, to get to this, and then we can take phi 2 with labels 1C and U to get to F of 1C and the U. And then from here to here we get via F of the left uniter of C for U. And analogously for the right unit. And I write them rather explicitly because I want to use them in the refinement of this definition. Also, we say that we have a strict monoidal functor. If we deal with a monoidal functor for which phi 0 is the identity on 1D and phi 2 is the identity member function. Phi 0 and phi 2 together are often called should be called the monoidal functor structure of F, but this is a bit long, so often one just says monoidal structure, which can be a bit confusing, I think. And also one uses the term only for phi 0 or then mainly only for phi 2 in case one is dealing only with one of them in some argument. And also you should notice that the two paths that I have here in this diagram are precisely the two possibilities to get from this object to this object by using only phi 2 and associated. And now remember that in the very beginning today, when I made this comment on the coherence theorem, I said it's important that the associator is invertible. Now, in the case of monoidal functors, it's actually of interest to relax the condition so that this is not necessarily an isomorphism. And then one gets to the notion not of a monoidal functor, but a lax monoidal functor. In this case, it just has a natural transformation in this direction and a morphism in this direction. Then previously, here we have isomorphisms in any case. Previously, also here we had isomorphisms, but now it's important that we have drawn them in this direction. They are only morphism in this direction and not in the opposite direction. Conversely, we say we have an oblux monoidal functor if instead we have a morphism in this direction and instead we have a natural transformation in this direction, and then we have again a consistency conditions, but then at least, and so, of course, in the opposite direction. And here, here in any case, we have still isomorphisms. Now, a last piece of terminology. If we have a monoidal functor in the sense I defined before, when we have isomorphisms, if we want to stress that they are isomorphisms, they also say strong monoidal functor. And some people always say strong monoidal functor, and when they say monoidal, they mean maybe only Lux or maybe oplux. But I will, when I say monoidal functor, I mean strong functor. And if they are Lux or oplux, then I will say this explicitly.
So for Lux, we still require the commutativity.
We still require commutativity, but in such a way that the morphism exists.
Okay.
So phi 2 only goes in this direction in the oplux case, in the Lux case only in this direction. And then, as a last comment before the break, put differently, a strong monoidal functor is a functor that is both Lux and oplux. Some people say bilux, where the Lux and oplux structure are inverse to each other. But there are interesting functors which are both Lux and oplux, but are not strong. And the most important class of this I will introduce after the break. We will not do much with them, but let me just stress that they're very important. Okay, which one? So the type of monoidal functor I was referring to is the following. It's called the Frobenius monoidal functor. Between two monoidal categories. And here I should add that the notion of Frobenius functor between categories also exists, and it's something that we will not talk about it. This is the same as Lux and oplux monoidal functor. So I have, from the Lux structure, I have a morphism phi 0 and a family phi 2. And from the oplux, let me denote them by phi tilde 0 and phi 2, phi tilde 2 in the opposite direction, such that the following diagrams in D commute. Well, we could write it in formulas. And with the diagrams, actually, you have to be a bit careful. I will explain why. But if you write in formulas, I think it's not transparent enough. So let me first draw this. We have an equality which looks like this. Large. And the second equality more space here. Which looks like this. Where we have to follow. So we start here with f of u, and here with f of v tensor w, and all of this has to hold for all u, v, w in C. And then here we have the morphism phi 2 u comma v tensor w, and here we have the morphism phi 2 tilde u tensor v comma w. So what does this go to? This goes to f of u tensor v tensor w, and here this goes from f of u tensor v tensor w to f of u tensor v tensor f of w. So actually here, different color. In order for this to make sense, as a morphism in a strict category, everything is fine. But when we deal with Laxenoid functors, very often we actually should be careful about the possibly non-rigid structure, and then we have to insert here the f of the associator in C for, well, actually the inverse for UVW. And then here, of course, we have to start again with f of u, f of v tensor w. And then here we will have phi 2, and here we will have phi 2 tilde. And this will, of course, be phi 2 tilde then for f of u. U and v tensor w, and then we will have f of v here and f of w here, and here we will have f of u tensor v, and this will be phi 2 u comma v tensor w. And again, we will have to insert associator here, namely now it's the associator of D for FU, FV, FW inverse. And for the other equality, we have instead here f of u tensor v, and here f of w, and end up with f of u and f of v tensor w. And from this information, you can reconstruct everything else. And as I said, I will not really use these. But they actually encode corresponding functors between bi-categories, and one category level higher. They have appeared in several different contexts in the last few years. Can I remark? Assume f from C to D is a monoidal functor, so strong monoidal. And we have the left adjoint, so we assume that it exists. How do I do that? Come P from E to C such that P is left adjoint to F. then automatically G comes with an oblux monoidal structure. And analogously, if F, it means the right adjoint. So if instead we have a G right adjoint, then G comes with a Lux monoidal structure. Now, even if F has both the left and the right adjoint, they might be different, and then one of them is Lux and the other oblux, but none of them necessarily needs to be strong. And one can say more about this, and I actually have not looked that up, but anyhow it would be too fast. But those who are interested can look up things in the book by Kelly on enriched category theory, which is in the list of references, and an exercise showed that this is indeed the case. So now we have monoidal functors, and of course we also have a notion of monoidal natural transformation. I will be short about this, it's just what you would expect. Let's say eta from a monoidal functor f to a monoidal functor f prime. This is, of course, a natural transformation. Which we call again eta from f to f prime, which is compatible with the structure, so such that the following diagrams commute. If we start from 1D, we can go by 0 to f of 1C, but we can also go by phi 0 prime to f prime of 1C, and between these two, by definition, we have the component eta 1 of the natural transformation, and to say they commute, and we'll not write it, and analogously, if we start from fu tensor fv, we can use phi 2 with component uv to get to f u tensor v, or we can use phi 2 prime to get to f prime of u tensor v. And then we can use eta with sorry. No. We have f here, so we cannot do that. But in order to get to f prime, what we can do is to use eta for u and for v to get to f prime u tensor f prime v. And once we have that, we can use vt phi 2 prime for u and v to get to f prime of u tensor v, and we get also from here to f prime eta, and also this should be commute. And if a monoidal natural transformation is invertible, we call it a monoidal natural isomorphism, and we say that if maybe I write that. We have a monoidal equivalence of categories between C and D, which are monoidal categories. This is a pair of monoidal functors. F from C to D and G from D to C, and monoidal natural transformations. Monoidal natural isomorphisms, which are just as for the unit and co-unit of an adjunction. One calls them eta and theta sometimes in this. I should have mentioned here that I have formulated this for strong monoidal functors. Analogously, you can do it for Lux and Oplux. For Oplux, then you have to reverse the errors accordingly. And just as an example or exercise, show that the category, which I denoted by vec k omega, which is vector spaces with the associator given by 3 cocycle omega, and the same type of category, but with omega prime, where omega prime is omega plus d chi for some 2 cochain chi, that these are monoidally equivalent. Both of them are monoidal categories, just the tensor product over K is tensor products, and then you have to find suitable functors which give you this monoidal equivalence. Now the notion, that's why I wrote this explicitly and not just said it in words, notion of monoidal equivalence is really very important because of the following statement, which I already announced at least once. Proposition or theorem, MacLane's coherence theorem, and MacLane's strictification theorem. We had a coherence theorem. Every monoidal category is monoidally equivalent to a strict monoidal category. And this is very important because in strict monoidal categories we directly have the graphical calculus, and we would like to use this as much as possible and get it's very often done without explicitly saying it. So we have a monoidal category which is not necessarily strict. We passively replace it by a monoidally equivalent strict monoidal category and continue about the proof. For full proof, you can look in the book by Cassel in chapter, well, the whole chapter 11.5 is the proof of the statement. And the idea is the following. We define a category on a W whose objects are finite sequences of objects of C. And maybe it's not worth writing it down without giving details. We define the morphisms of the category by giving first a prescription on objects that you define inductively via the lengths of these sequences, and then show that this actually can be extended to a functor. Well, extending this to a functor and defining the morphism at the same time, so to say. And then you define the tensor product on this category W, and then you show that the monoidal category you get here, there's a natural functor between this one and the original one, and then you show that it's a monoidal equivalence. And this is a bit lengthy, but the proof is, I think, very clearly described in particular in this book by Cassette. Now, sometimes this important statement is used to state erroneously that we always can just work with strict monoidal categories and don't have to care about non-strict ones. This is certainly not true as it stands, but even when it's used, it's usually not really used, because when you replace a monoidal category by a strict monoidal category, the strict monoidal category somehow remembers something about the non-strictness. And this is gives in particular rise to the following concept. So let me first write that under the equivalence from C, maybe I call this WC to make it clear that it comes from C. Non-trivial information about the associator of C is preserved, or about the tensor product, maybe I should write it like that. The tensor product that you define here is, of course, defined by using the tensor product of C. When you just say, I take this category as strict, that's not the same thing as saying it's strictified, because if it's strictified, then I have to, in principle, to describe it in that way. And of course, to do this in practice would not be a good idea, but actually it's not needed. You see it at least in the semi-simple case as follows. So we have, as a remnant of the associator, you have the following. Assume we are in an abelian category, or in any category where the notion of simple. No. Let's directly assume a semi-simple and linear, so that the morphism spaces are vector spaces. And let me write H for C and H lambda mu kappa for C of y lambda tensor y mu y kappa. So these are the representatives for the isomorphism class of simple objects. If I tensor this over K with H lambda prime mu, with all these labels in capital lambda and sum over mu, then there is a morphism, an isomorphism between this tensor product and the tensor product H mu lambda double prime kappa tensor over K H lambda prime mu. And then you can define what's called the 6 J symbols. I often use this name. Of other people call it fusion matrices, or also just F matrices, because often we use the letter F for them. As matrix blocks of the linear map given here with respect to chosen bases for all these morphism spaces. And of course, the numerical values you get for these depend on your choice of basis in general, but there are specific ones which do not depend, and they are often particularly interesting. And they can, for example, be used when you try, what I would not want to try, to classify certain classes of the labels. And let me just, because this is used in very many explicit calculations, and also because if you look at the details, then sometimes the exposition is is somewhat sloppy, and also because if you take say 4 papers using them, then you have at least 3 different conventions for them. So this is my convention, which actually is different in one respect from convention of many others, but it's the one I'm used to. So we take a morphism alpha in a basis I just collectively call alpha, beta, and so on, and another one beta. Beta is in this space here, so we have mu here, and alpha is in this space. Let me see. No, I did it differently. No, lambda prime. I use here as somewhat different notation than here. I should have changed it here. This should be lambda, and then so we have here lambda, and here we have mu, and here we have kappa. Let me see. Lambda, no, it's one. Lambda mu kappa is here, and lambda prime, lambda double. Nobody complained. This should be lambda prime, lambda double prime. I shouldn't have the same label twice. That's what confused me now. So this I compare. So this is a basis of the space y lambda tensor y lambda prime tensor y lambda double prime to y kappa. If nothing would be remembered about the associator, then this would be just the same as taking a basis delta for lambda prime to nu, and then gamma from lambda double prime, nu lambda double prime to kappa. So this would just be, well, at best some permutation, but of course these are just bases in this one morphism space, where this is really the same object in the different tensor products in the strict category, but they are built up from different pairs of bases in the underlying morphism spaces here, and therefore they will in general be different, but they are bases, so there's a basis transformation, and accordingly there's the sum over all gamma, should start with mu, gamma and delta, and then there will be some coefficients f. And my notation for that, just in case, no, not just in case, I will not really use them because it's a pain to always write these labels, but my convention is that these here are the matrix multi-labels. So for fixed, lambda, lambda prime, lambda double prime, kappa, we have this as a square matrix with, say, rows labeled by this and columns by this combination. And and you can say a lot about these. For example, you can you can express these. Well, not if you, in addition to linear and semi-simple, require that a monoidal unit is simple. Directly as a morphism from, well, you can express them as a morphism, endomorphism of the unit, but and if that is simple, then you no, sorry, you can you assume that it's that the monoidal unit is simple, and then these numbers can be interpreted as morphisms from the monoidal unit to itself, and you essentially they are obtained by combining, well, manipulating these graphs, and there are many papers about that, but some relevant notation and statements are collected in appendix of a paper by myself. A student in Stockholm who has not yet got his PhD, but next week this time we will. I hope. So that's all about section 2.4. After 2.4, in principle, there should be section 2.5, which would be about not monoidal categories, but graded monoidal categories, where graded hyphen monoidal, so not monoidal categories which are graded. It's not the same thing, that notions, but I decided to skip this. If there's time at the end, or maybe next week, but I don't think so, I will present it. Otherwise, it has to wait until another time. For instead, I will continue with 2.6, which is about rigid pivotal structures. And I stressed when I started with monoidal structures that both in the example of cobordism categories and in the example of vector spaces, they have more structure than just category. It was a tensor product, but there is still more, and that is in particular what we are considering now. And let me just indicate this briefly in the case of these two examples. So we look at cobordisms. And we call that if you have an oriented manifold M, we also have a manifold M bar, which is the same underlying manifold, but with a reverse orientation. And then you can observe that if we have M, such a manifold here, an object so a D-1 manifold, then we see that the cylinder over M, which by definition is just M times an interval. So this is a D manifold, and therefore potentially a cobordism, a morphism in our category. But it's not clear what it is, because you immediately see that this can be regarded or made into cobordism in 6 different ways. I think this is true in any dimension, but to show it, actually the case D = 1, which we started with, is too trivial in this context. So let's take D = 2, and let's take M to be the circle. And then, no, we don't need this at the moment, but, no, we, only for drawing this. So here, in generality, I can say either I have the identity on M, where I start with M, then have the cylinder and end with M, or I think of this as a morphism, which I call dm, which goes from M bar tensor M to the empty set, or as something I would call bm, which goes from the empty set to M disjoint union with M bar. So this depends on which of the 2 boundary components of the cylinder here we interpret as incoming or outgoing. And we also can interchange the role of M and bar, so we get 3 more of them. And in this particular case, the identity on M would be what we usually call a cylinder, whereas Bm, and now not distinguishing between M and M bar for simplicity, for brevity, would look like this, whereas if we draw from left to right, which we do for cobordisms, or we have something. And then from this picture, and analogously you can see it easily in general case, it is immediate that they have some relations between them, and I just draw the relation for this particular case, and do not write the formula because we will have the formula. If I take the cobordism, which is the disjoint union of this cylinder and this cylinder, and compose it with the cobordism, which is the disjoint union of this cylinder with this cylinder, and then remember, but even what I'm saying is not correct. The cobordism is not a manifold. Cobordism is manifold modulo homomorphism. So this we should really think of this as one way to look at that. And even here, I would not have to draw it like that. I can draw all of them as I like. I only have to say what is to specify what is ingoing and what is outgoing, because we not only have a manifold with boundary, but we also have to specify embeddings of the boundary components. And if it's incoming, this has to be orientation preserving and outgoing orientation reversing, or the other way around, depending on your conventions. And but it's just suggestive to draw it like that. In any case, no matter how suggestive it is, if this is the same as this circle with the same embedding and analogously here, then these two manifolds represent the same covariance. So they are equal as morphisms in our category. And similarly, if you take C to be vector spaces, then we have morphisms for any vector space X. Actually, we have two of them, two versions now of D, either from the dual of X, tensored with X to the underlying field, or the other way around, where we simply say that let's use Xi for an element here, and small x for an element here. We simply send this to the number Xi of X, and analogously here the other way around. Usually one does not distinguish this, but it's actually sensible to do it. This we have for all vector spaces. If, as I normally assume, we deal with finite dimensional vector spaces, then I also have morphisms in the other direction. To be precise, from K to X tensor X star, respectively to X star tensor X, which are given or can be given as follows. I take a number. Now I need, let me call it theta, even though it looks like similar to the Xi. A sum over I. This is a finite sum because we are finite dimensional over Xi tensor theta times Xi tensor Xi, where this is a basis of V of X. And this is the corresponding dual basis of the dual vector space. And analogously here, just do it the other way around. And then you can check that actually we have identity on X, tensor dx composed with bx, tensor identity on X is the identity on X, and similarly dx tensored with the identity on X dual composed with identity on X dual, tensored with dx is the identity on X star. And actually for checking this, I don't write it out to save time, it's easiest to recall that for finite dimensional vector space, X tensor X star is isomorphic to the endomorphism of X. And the Bx that you have, that you define this way, actually under this isomorphism is mapped to the identity on the endomorphisms. And actually this also shows that while in this description here we have chosen a basis, the resulting linear map X is actually a basis in the set. It's clear because we use the basis and the dual basis of the dual space, not an arbitrary basis of the dual space. And then you show this, and then what you call these maps, well, I call them right evaluation respectively left evaluation and these here right co-evaluation and left co-evaluation. And then after the break, we will define the same notions now for an arbitrary and general monoidal category will not have admit such such morphisms satisfying these relations, but some of them do, and they are of particular interest. Let me just, there's still some time, introduce some further terminology. These identities here are called snake identities. Well, we have, I wrote them for B and D. There are corresponding ones for B tilde and D tilde. Some people instead call this zigzag moves or identities, and some people call them Zorro moves. And all of this comes from the fact that we have something like that which we straighten out, and if we, as we will do after the break, use graphical calculus for monoid categories which are admit such morphisms, then we will again look something like that, except that we continue to draw morphisms of stuff. And maybe two further remarks about notation or terminology, that I call this right and this left. That's my convention. There are two possible conventions, and in the literature, both of them are, so calling this left and this right is equally frequent, more or less. Also, there's a notation which I will introduce, and sometimes the notation I use for this one is used for this one and the other way around. So there are altogether 4 conventions. You can find all of them in the literature. And then you could ask why calling them B and D. I'm not sure whether this was the original reason for it, but some people call B also birth and D death. Because here something vanishes and here something comes out of the bucket. Okay, let's have another break.
Joins, or you have some better arguments? I prove it.
Together with the statement, which I should have made at some time, but which I didn't, and then
okay.
That any equivalence can be promoted to an adjoint equivalence.
Ah, okay. Yeah, I just know how to do it.
So if you take an equivalence, two functors need not necessarily be adjoint,
okay.
but they are isomorphous. Natural. You have natural isomorphism, and you can modify them. Such they become. I have to look. I would have to look up the precise statement, but together with that, you'll see it.
Okay. That's.
或者说一个 correlative function 本身是某一个比如说 set 找一个这种方式出来一个来帮助，就是对应是 x， 然后用这个常用的那套方程也算这个方法。因为有一个是我跟 CT 用一个 conformal symmetry 得出来的一个什么样子 ？OK， 那就是用。就比方说我考虑一种就6.2的那个 CFD， 然后它100比积分的1000的光性的，那它只有这个我是改长的吗？就是那个它也有点什么 CFD， 就现在那个学院学的那个我们还有那个它里面的。大概是有送的，然后呢，这个还相当于都是给这样一些这个群里面的能量，给问积分，这么正负离子分去，那我们是一个3点，那个还有什么？那是我是有点少的。这块来算还是，我就对这方面，我3遍，我3遍，但是，做的，因为我在3点钟开始，然后3点，是2遍，我得到一个。OK， 那怎么对出来那个 surrounding 体现？这个是那个 Lagrangian， 有那个 Lagrangian 的方法，是一个然后或者是其他的，对，那个是一次，然后是一个偏方的先把那个热词经典的场方法就来这个算出来的。就是经典高数有 context， 这种观察数只有 context 之后才会出现的，是这个 context 经常哦，对，就这个 OK， 然后但是它那个之后变成是3个位置产生这样一个因素，谢谢。然后再用这个具体的标识化的形式，再去这个去讲。After the conversion statement is convenient, we have time tomorrow or maybe next week. So let's go. Do we have course on next week? I should announce this. There's no lecture on Tuesday because of the holiday, but instead we have it on Wednesday. I see. So how about we discuss on Wednesday? Fine with me. After the lecture. Not directly after the lecture. Actually, it starts earlier because I have a Zoom meeting afterwards, but that will not be long, so there's still time to discuss. So the Zoom meeting is at 4. So I will end before 4 o'clock. And in principle, the Zoom meeting is scheduled for 2 hours, but I'm very confident that it will not take long. So at 5 o'clock, I wish or maybe a few minutes. Oh, sure. And then we actually have a problem because I do need the laptop for the Zoom. So we cannot. So if we convert, then I would have to use your laptop for that Zoom meeting. But then I have to use it for the whole time it takes. Okay. Thanks. We should have just use your computer for the. Yeah, but now maybe we can. next time.
Maybe you can do it next time. That would make things easier. So you will need this password, which you probably don't remember anymore. And I don't either. So I will give it to you right now.
And also the username.
Yes.
For that. Two more times.
Because the entry. When do we start? Quarter past or 10 past?
10 past.
10 past. Okay. I just send it to you.
There's no kind of change next time, next Wednesday.
I will announce it. And also that I should. I will do it afterwards. There's no time now.
Let's see then.
Yeah. The touchpad does not fully do what I want. We can continue with the review. So we now abstract from these two examples. We give the following definition or definitions. Steps. We say that right dualizable or also right rigid object in a monoidal category C this is an object X in C for which there exists an object Y in C and morphisms Bx from 1 to X tensor Y and Dx from Y tensor X to 1 such that we have analogs of what I erased, namely identity, the same formulas really, except that just once now I do not assume that C is rigid and write out the associator, but in what follows then I will suppress it again. And now I just call this Y because I only require existence here. We have these two equalities, and this should be the inverse associator. And we say that the category C is right rigid monoidal category, and we do not always then say monoidal if and only if every x in C is right rigid as an object. And in particular, in the older literature and pure category theory literature, instead of right rigid, one also says right autonomous.
The first equation is dx, right? The third one, dx.
It should be
dx.
D. Thank you. And oh wait. No. We need B here. Here was B. Here it was correct, and here it was correct, and here it was correct. Let's see. Yeah. If I once I have the graphical notation, okay, it's the right thing. And analogously, we say the left dualizable or left rigid object is an object together with corresponding morphisms B tilde. When object Y tilde and B tilde, D tilde, which now go from 1 to Y tilde tensor X, respectively from X tensor Y tilde to 1, with similar identities. And I don't write them down. And then we say that C is rigid or autonomous. If and only if C is left and right rigid. And of course, again, also we can define this analogously also for objects. And just like in the vector space case, we call them co-evaluation and evaluation. And in my notation, I call them right and left co-evaluations and evaluations. And correspondingly, I call Y maybe with this notation here, we write Y equals X with a V here. We call it the right dual of X, and the Y tilde we call the left dual and put it on the left. In principle, one should better say right rigid dual, because there are more general notions of duality. But like symmetry, maybe after symmetry, duality is used for the largest number of different things. It's not common to say explicitly rigid dual. Maybe an example, a partial example. If you remember example 213, then we looked at the category of endofunctors of small category. So objects are endofunctors, morphisms are natural transformations between them, and it is monoidal with tensor product given by composition. I think I already said that. If not, I say it now. And now actually there is, one has to be slightly careful about this. Well, what does composition mean? Well, we want to define F tensor G for two such functors, and depending on our conventions for composition, we could say this is F composed with G, but we also could say F tensor G is, so first F and then G, so we could also take this convention. And what I will say now will depend on the convention. Namely, if we use this, then the right adjoint of a functor F, if it exists, is left dual F in this category, and analogously the left adjoint of F, if it exists, is right dual to F in this category, in this functor category. And people who prefer this definition will not like that here right and left are interchanged. So they would define left and right for dualities in the opposite way. But the way out is to use this tensor product. So that this is not really a notation independent argument. Exercise, important exercise. Maybe someone does this. Check this. Look up the definition of left and right adjoints and the definitions here and see whether this is correct or whether I'm mistaken. I didn't look this up anywhere. I just wrote it down. I just looked at the definitions myself. And then, of course, usually, as I said, we work with strict categories, so we do not write them. We will use the graphical notation, or want to use the graphical notation. Then, importantly, in the title of the subsection, I wrote rigid and pivotal structures, but this is a bit misleading. I just could not come up with a better name. Rigidity is not structure, it's a property. So duals are not property but structure. One way to formulate it is as follows. Assume for an object we have two different duals, say right duals. Analogously, I can look at left duals and call them u, v, du, vu, and the other one u with a different symbol, and maybe delta u, beta u, b right duals of u. Then u, v, and u with this other symbol are canonically isomorphic. What do we mean canonically? They are isomorphic. Well, but there is in particular unique isomorphism. Say call it phi u in this direction, such that if I start from uv tensor u and use phi and the identity to get to this other one. Here I can use u to go to 1, and here I can use delta u, then this commutes, and an analogous triangle, co-evaluation instead of evaluation. And accordingly, because, well, this means the left dual or right dual of an object, if it exists, is unique up to fundamental isomorphism. And therefore, we also talk about the left dual or the right dual of an object. And this is a very important result because together with further lemmas, which tell that one can choose duality in a nice way, and then because of the uniqueness, we can use that always. Or if we by some given construction get duals, and there are another platform, we know that there are equivalent ones which we can replace them, and usually want to replace them. Lemma dualities, rigid dualities, if they exist, are compatible or can be taken to be compatible with the monoidal structure. So first of all, compatible with the monoidal unit. So we can assume that the left and right dual, if they exist, of the unit are equal to the unit. This is one of the instances where we actually use equality between objects. And to be precise, we should do this only if C is strict. Otherwise, we would say they are isomorphic, but not in an arbitrary way, but isomorphic while they exist. The unit of what the one unit, the one component of the unit. Oh, did I say one thing? Let's put this in somewhere. Or maybe I forgot to write it down. No, it's covered by what I said, so I don't continue. So compatible with the unit and compatible with the tensor product, meaning that if we first take the tensor product and then take the dual, well, we have to change the order. But up to that, we can take the duals factor-wise, and analogously for the left duality. And again, equality and not just isomorphic. Isomorphic they are always, and that we can choose this in a way such that this is an equality. This is not hard to prove in terms of formulas, but it's even easier if you use graphical calculus. So I prefer this for some minutes. And this another lemma says that if C is rigid, so both left and right rigid, then we can take those dualities in such a way that the left dual of the right-dual object is equal, not just isomorphic to X, and analogously the right-dual of the left-dual is. And just to mention the idea of proof, and again, this can be more nicely be done with graphical calculus. If you consider the morphism, you take the left evaluation for the right dual of X here, and you compose this in this way. And here you take the identity on the left dual of the right dual. This is an isomorphism by simply using the snake identities to give an explicit inverse, two-sided inverse. And then using the lemma here, we can absorb this an isomorphism between this object and this object, and then we can absorb this via the uniqueness statement, so that we change our conventions or our definitions of the dualities to get this. Now, this is easy. It's still easy, but not as easy that you can impose this property and this property simultaneously. And each of them is nice, but together they are very nice. Side remark before we come to the graphical calculus concerning vector spaces. And up to this point, I have managed to use this notation vec k normally for finite dimensional vector spaces without having to indicate this in notation. But now I want to say something also related to infinite dimensional vector spaces. And the reason for doing that is that if I do this in a file, then I would use a capital V for all vector spaces and a lowercase v for finite dimensional vector spaces, but in the handwriting I cannot distinguish between them. So now this is the only time I really have to talk about this. So lemma says that, well, let me directly announce that I will have a remark on the statement, because it's sometimes interpreted in a somewhat inappropriate way, including by myself. A vector space admits dual, and it's both left and right dual. Remember when I had this example about vector spaces, I had these and d tildes, but they were essentially the same, except for convention on the ordering. let's meet in the same category. It's in principle unnecessary to say this, but this is related to the comment I will have. So in the category of either finite or infinite or general vector spaces, it works only in the finite dimensional case. So V is finite dimensional. Let me write it that way. So V is in this category. And let me briefly indicate the proof. One direction is clear from the example. I have assumed in the example finite dimensional, and I have at least told you that I do get a dual. And I almost gave all relevant details. Now in the other direction, that I necessarily need finite dimensional is the following. Assume that the right dual exists. Right, for example, then you have this co-evaluation for V, and in particular, if you apply this to the number 1, you get a vector in V tensor V star. And it follows from this that actually you can write BV of 1. Well, it's no, it's equivalent that you can write BV of 1 is a sum. I write explicitly like that, so this is an integer, finite sum, and now I use a different notation. I think I wrote xi, but let me write bi tensor beta I, where I can take these to be bases, but actually I don't have to use the databases. I only have to use I can write this as a finite sum for suitable elements in V and V star, and then using the snake identities. Here I should write dots. One can see that this implies that an arbitrary vector in V can be written as a sum over I from 1 to n bi multiplied by beta I of V. Is a number applying an element of V star to an element of V. And this holds for any vector in V. Now this means that this is a finite number of elements, that we have a generating set, finite generating set of our vector space, and therefore the vector space cannot be infinite. Remark, and I don't write the details.
So you need to proof pendency. Because don't you assume already finite sum by taking sum from 1 to n? N is not finite.
For some.
No, it can be infinite dimensional, but this is finite sum. Finite sum is presumably.
I do not assume at this point that.
And then you derive that it's
yes.
finite dimensional.
Yes. So there are some details here which I.
So it really depends on the definition of the tensor product. So an element can be written as a finite sum. Right?
That I should have said. Thank you. So definition of the tensor product. This is the tensor product for K, and by definition of I didn't write it here. by definition, the elements in the tensor product vector space are finite sums of tensor products of vectors in the individual spaces. And now the remark is the following: that even though it's really not necessary to say this, because I have defined duality as, well, not yet as a function, but almost. In fact, there is still a substitute of duality for infinite dimensional vector spaces, and this is that there is anti-equivalence between, which one still denotes by star, between the category of all vector spaces and the category of pseudo-compact vector spaces, where there's a definition of pseudo-compact, which I will not give you, but the relevant thing is that you get these vector spaces as projective limits or inverse limits of finite dimensional vector spaces, whereas you get all vector spaces as injective, direct limits of finite dimensional vector spaces. Using this fact, you can actually make statements about infinite dimensional vector spaces which are similar to statements you would, because of this lemma, possibly only expect for finite dimensional ones. And let me give a reference here. There is a paper by Guen and collaborators, which I will put in the references. But that's only a side remark. It turns out to be relevant when you try to understand interesting categories which have infinitely many isomorphism classes of simple objects. Now graphical calculus. And I think I can be quick about that. A lot of this, the rest of the lecture. Now I assume that I have left or right or both rigidities, and I just introduce a graphical notation. So dx is a morphism from xv tensor x to the tensor unit, which is invisible, and I abbreviate this this way. And bx, which is a morphism from the tensor unit to x tensor x dual, I abbreviate it in this way. And analogously for the tilde ones, let me just write it this way. This I denote like that, and like that. So here we have left dual of x. Here we have left dual of x and left dual. Using this, the snake relations look as follows. So here I do it for the right duality better. So here I would start with xv and end with xv, and I get the identity on xv. and here I have bx and dx, and here I would have in the other order bx and dx, and get the identity on x. And for the left duality, just again mirroring everything with respect to a vertical line. Comment. Many people like to use such graphical calculus and put arrows on the on these lines. I do not put arrows on lines. This is really an abbreviation for these morphisms. So this is a morphism and not the direction of the line. Why? Well, if I would do this and take it seriously here, then I would say here I go up, but then here I go down. So going down means that instead of x, I have x dual. But if I now switch again, then I get x double dual. Whereas graphically, I get again just an arrow going up, and in general, x double dual and x are completely unrelated. In interesting cases, they are very closely related, but we come to that. So in general, not. And you can easily make mistakes with this, in particular, if you have categories that so-called forbidden sure indicators are not trivial. And then how can you use this? Well, just and the two lemmas that we had. There was a lemma 267, which was about uniqueness. So assume you have u as I do it here, and you have this other duality where I call the relation delta u. Now we need also some notation for that, maybe with a different arrow. And analogously for the co-evaluations, then we define phi u. This is precisely the phi u that I was talking about in 267. This would be just this morphism. So what is this? Here we have x. So here u. Here we have u one type of dual, and here the other type of right dual. And this is clearly an isomorphism because its inverse is just given by this. If you compose those in any order, it uses snake relations both for this duality and for this duality. Then you see that composed to the identity. And therefore, this is an isomorphism. And then you can easily check again graphically these triangles that diagrams that have to commute simply amount to something like this. Where now, however, like this, or put upside down, where you have, say, if you have the duality like that. So this is easy to see, and similarly in the proof of 269, this I have a separate number. Maybe this was even 274. No. It should be maybe, but I'm not sure. So this was about compatibility with the monoidal structure. Now for the tensor unit, this is invisible, and if I dualize something invisible, then it stays invisible, so there's nothing to be shown. And for compatibility with the tensor product, assume that you have u bu and dv dv, and then you just define on the tensor product this in terms of this morphism. So this would be U, V, and V dual, U dual. So this is the evaluation for U tensor with identities and then composed with the evaluation for V, and analogously for V. Suitable labels here. And suitable co-evaluations. And then using the snake identities for U and for V, you see that also this satisfies the snake identities. Another remark in which I use the graphical calculus, which would be easy to write in formulas, but it's I think nicer to have it graphically. Assume M is say left module, and over some algebra A in a rigid category C, or actually I only need that this is right rigid, then MV has a natural structure of right A module. So really the dual of the underlying object M dot. And how do we do that? Well, we have an action of left action of A on M, or more precisely M dot, but we want to get a morphism where we start and end up with M dot dual, and for that we can use dualities, and then we have our A here, and then you can check that it satisfies the properties of a right action, and similarly if it's left, if it's left rigid, then the left is a natural structure of no, I should write that. Say N equals N dot rho, a right A module, then the left dual has a natural structure of left A module by just using analogously the left duality. So here we have our N, and now we start with a right action, and what we get is left action. And what do we can do a bit further? Another remark. I will come back to 278 later. I decided to have this a bit earlier than originally planned. A remark. If I have dualities, then there is an impact of functors. So we have an anti-equivalence. It's called just right duality between C and its opposite category, and also left duality, assuming that they exist on objects. Yeah, on objects, they are what we have. And on morphisms, we have the following. So FV for F, the morphism from, say, X to Y. FV is a morphism then from, it's in the opposite category, so we have Y and X. And we simply get it by composing with the right duality and analogously left dual, where we have left duals here and here. Oh. Should start with F. We're not right. It's again from X to Y. Really, this is compatible with identities. So the dual of an identity is just the identity in the opposite category and compatible with the composition. And then finally, for today, following lemma. If X is right rigid, then the functor tensoring from the left with X is left adjoint to the functor of tensoring with X, and tensoring from the right with X dual is right adjoint. With X, and there is a similar statement for F left rigid, then tensoring with the left dual is right adjoint. So tensoring with X and tensoring from the right with the left dual is left adjoint. And this is again easily seen graphically. Assume you can look at morphisms from Y tensor X to Z. So we are now tensoring with X from the right. Then we get morphisms to what we need for having tensoring with XV as a right adjoint as follows. We start with F going from Y tensor X to Z and map it to in this way, respectively, if we have a morphism on this side from Y to Z and the XV, we send it to, again, just using the right duality. Then we have X here. And clearly, just by the snake identities, these are two-sided inverses. And That's it. Analogously for the for the left rigid case, and then finally corollary of that. If C is rigid, then this means that tensoring with x in any order both have the left and the right adjoint for every x, and this means that well, I suppose left and right adjoint. And in particular, if C is also abelian, then together with the statement that we had somewhere, I didn't write it down, that existence of left adjoints and right adjoints is related to left and right exactness. We have that they are not just right exact, but even exact. Finally, an exercise which I don't write down. You can try to show that any monoidal functor, strong monoidal functor between rigid categories, precisely preserves left and right duality. And we can also try to see what happens if it's not strong, but only right. Okay, that's it for today.